Okay, so yeah, please remind me to record. Okay, so here we have the tree, right? And it says, if outlook is overcast, predict yes. If outlook is sunny, check humidity. If outlook is rainy, check windy, right? Okay, let's compare that. How does this look? If outlook equals sunny, which is over here, then do what? Check humidity. If humidity is high, predict no. If humidity is normal, high, predict no. Normal, yes. Okay? If outlook is equal to overcast, just predict yes. Outlook is equal to overcast, just predict yes. If outlook is equal to rainy, check windy, and so on. Okay? So that's another display of the tree right here. Okay. So that's J48, by the way, but I want to explore this other one called OneR. So let's look at this data here. So how does OneR work? OneR only focuses on a single variable. So we can choose from any of the 4 input variables. So that's outlook, temperature, humidity, and windy. So let's start with outlook. It's the first one in the first column. So let's start with that. So what we do is we look at the different possible values of outlook. So what are they? What are the different possible values that outlook can be?
Sunny, overcast, and rainy.
Yeah, only 3, right? Sunny, overcast, and rainy. So, okay, so what we do is we're only focusing on outlook. We're ignoring all the other variables, but we want to make a rule. We want to predict whether people are going to play or not. So just focusing on outlook, the rule has to be something like, if outlook equals sunny, do one thing. If outlook equals overcast, do something else. If outlook equals rainy, do something else. That's the way the rule has to look, because there are 3 possible values for outlook. So, so what should we do? How should we make the decision for each of those possible values? What should we say? So I color-coded it, right, according to the different values of outlook. So sunny is yellow, overcast is gray, and rainy is green. So if it's sunny, then what should we predict? So how do we decide? How do we decide what the rule should be if it's sunny?
We see the yes and no in the play, and if there's more no, then we predict that we won't play. Yeah,
right. So we look at the, for sunny, we only look at the yellow, in other words. We say, how many times did they play and how many times didn't they? Or in other words, how many yeses and how many nos? So if we look at only the yellows, I see 2 yeses and 2 nos, right? No, sorry. Why did I write? Oh yeah, right. No, 1, 2, yeah, 3 yeses and 3 nos and 2 yeses, right? Does everyone agree with that?
Yes.
Okay, so what should we predict? Well, if there's 3 nos and only 2 yeses, we should predict no, right? Does everyone agree with that?
Yes, Professor.
And then, is that rule perfect? I mean, if we, within this data set, is that rule perfect? That means if we predict no whenever it's sunny, will we always be right?
No.
No. How many times will we make an error within this data set?
2/3.
2 times.
We'll make an error 2 times, right? Because there are 2 yeses, right? And we're going to predict no, right? And there are 2 yeses, so we'll make an error twice. That is, if we say when it's sunny, they're not going to play golf within this data set, that's wrong twice, right? Does everyone agree?
Yes.
And then out of how many cases is it wrong? Well, altogether, the sunny cases, there's 5. So we'll make 2 out of 5 mistakes. Okay, so we write that over here. How much error was there? 2 out of 5. Okay, so everyone understand this first one?
Yes,
Okay.
Professor.
Okay, then we do the next one. Because we have to do it for all the different possible values of the outlook variable. So if it's overcast, what should we predict? So that's the gray ones. So for overcast, we have yes, 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 and yes. So obviously, what should we predict? There's 4 yeses and 0 nos. Obviously, we should predict yes. And then how much error is there? There's no error within this data set, right? Does everyone understand that?
Uh-huh.
Yes.
Maybe I can make it a little bit, just a tiny bit quieter here. Okay. Okay, so in that case, there's 0 error within this data set. Okay, and then the last one we have to deal with is the other value, which is rainy. And if it's rainy, that's the green ones. So we said, let's see, yes, there's 1, 2, 3. So there's 3 yes, and there's 2 no. So 3 yes and 2 no. So that means we should predict yes. And then how much error is there? 2 out of the 5 cases where it's rainy. Does everyone understand this?
Yes.
So how much error did we make here? Well, we had 2 errors here, and we had 2, and the total number of elements in our data set was 14, so we made 4 out of 14 error. Okay, does everyone understand that number? Does everyone understand that number?
Yes.
Okay. All right, so that's for, we just chose Outlook arbitrarily to make the predictions. So we want to do it for all of the variables, not just for Outlook. We want to check for all of the variables. So we can do the same thing for temperature, which I did here. So temperature, how many possible values does temperature have? Three, right? Hot, mild, and cool are the only things that temperature can be. So if temperature is hot, I put it red. So how many, so what do we have? We have 1 no, 2 no's, 2 no's, and 2 yeses. So 2 no's and 2 yeses. So that's a toss-up or a tie. So you can use it, in that case, you just have to predict something. So you choose either one. So I chose yes. So you could have chosen no, doesn't matter. In terms of, it's a tie, so you can't decide. So how much error is there? There's 2 out of 4. Okay, next thing is, what if it's mild? So if it's mild, it's yes, 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 yes. That's 4 yeses and 1 no. 4 yeses and 2 no's. So we predict yes, because it's 4 against 2. And then there's 6 cases, so it's there's 2 errors out of the 6 cases. And then if it's cool, we get 3 yeses and 1 no. So we predict yes, and that's 1 out of 4 errors. And then the total error is 5 out of 14. Does everyone understand that?
Yes, Professor.
Okay, so we end up here with this. So for Outlook, we had 4 out of 14 errors. For temperature, we had 5 out of 14 errors. For humidity, we didn't do it, but we could do it, and we would get 4 out of 14 errors. And for wind, we could do it, and we would get 5 out of 14 errors. Okay, so now the question is, if we're just going to choose one variable to make our decision, that's what the OneR stands for, which variable should we choose? Well, we should choose the one that has the least error, that generates the least error, the least total error. Well, in this case, there's actually two that generate the same least total error. So you could choose either Outlook or, either Outlook or humidity. Okay, and that's how OneR would work. So if I chose Outlook, I would say the rule would be, if it's sunny, no. If it's overcast, yes. If it's rainy, yes. And that would be our rule. That would be the entire rule. And if we run this in Weka, you can see when you run it that you get this rule. They chose the Outlook, and it's if it's sunny, no. If it's overcast, yes. If it's rainy, yes. Okay? And how much error does that give us? How much, or let me go here. How much error does that give us?
5.
No, Outlook gives us
4.
4 out of 14, right?
Yes.
In this data set, right? We're not talking about some future data set, just within this data set, right? It gives us 4 out of 14. So that's what this says, 4 out of 14. So what that shows up where? Here. The correctly classified are 10 and the incorrectly are 4. And if you work that out, I guess you get 71% accurate and 28% inaccurate rate. Okay, is this clear? Okay, so that's how OneR works. So how do you think we go from OneR to J48? Let's see J48 again. J48 is here. Let's look at the tree. So how do you think we go from that to J48? Not that straightforward, but you might come up with the idea. So with J48, we seem to start with the same outlook. Why did we start with this one? Because we found that it was the best, or it was a tie actually between that one and humidity, but we chose this one. We could have chosen humidity, I guess. It could have chosen humidity, I guess. So we chose this because it was the best one. And what does it mean that it's best? It means that basically the idea is that it makes the least amount of errors, which means that if we predict overcast, we talk about the purity of the result. The purity of the result is when we predict overcast, we get, let's see that. When we predict overcast, we get all yeses. So we get a completely pure result of all yeses. That's sort of the ideal. That's the best thing that could happen, right? Now here, when we predict, if we check rainy, we didn't get a completely pure result. What did we get? When we did rainy, we got 3 and 2. We were going to predict yes, but we don't get all yeses. We get an impure result, right? Is that clear?
Yes.
Okay, so we get this kind of impure result for rainy. So what we do is, then we say, okay, for those elements, the ones where outlook was rainy, so that's not all of the elements, that's only where outlook was rainy, that's only the green ones here. For those only, we say, okay, is there some way that we can split that up to obtain a more pure result? So we say, okay, let's check when outlook equals rainy, just these green ones, let's check windy. How did we decide to check windy though? Why didn't we check, humidity, or why didn't we check temperature here instead of, like, when it's rainy, we're just looking at the green ones. Why do we choose to check windy next, not humidity next, not temperature next? Why? Why do you think we might do that? What do you think we did? Anybody? Anybody see where this goes? So what we do is we reduce our data set only to the green ones. Then we do the same thing that we did before with OneR. We look at temperature just for the green ones, and we see what kind of result we get. Like, how many errors do we get if we look at temperature just with the green ones? How many errors do we get if we look at humidity just with the green ones? How many errors do we get if we look at windy just with the green ones? So, for example, if we check temperature, what happens just with the green ones? So what do we have for temperature within the green? We have two possibilities, mild and cool. I don't think we have yellow, do we? Within the green? No, of course not. Wait, what do we have? We have mild, cool, mild, mild. Yeah, we only have those two possibilities. So we check. When it's mild, there's yes and yes and no. So what would we choose if it's mild? We would predict yes, right? Do you understand? Sorry, mild is yes, mild is yes, mild is no. So if it's mild, if temperature is mild, what should we choose? Just within the green.
Yes.
Yeah, we would choose yes. And how much error would we get then? Yes,
One-third.
yes, yes.
Oh.
Two no's, right? Oh, sorry. Mild, sorry, what am I doing? Mild, yes. Mild, yes. Mild, no. Yeah, right. 1/3, right? Or 1 out of 3, right? Right. And then we would do the same thing for cool. And so we could measure, just like we measured the error here, we could measure the error if we use temperature on the green ones. And then we could also measure the error if we used humidity on the green ones using the same kind of process. And then we could measure the error if we used windy just on the green ones. And then we would decide, well, just on the green ones, which gives the least error? And it turns out, I guess, that windy gives the least error. What does windy give? So for the green one, we have two possibilities, false and true. So if it's false, we will predict, let's see, there's yes, yes, yes. So if it's false, we'll predict yes, and we'll get no errors there. And if it's true, we'll predict no, and it's true both times. So we get no error if on the windy. So that's probably why that the next node, when it was rainy, that means if we're only looking at the green ones, that's why they chose windy here. Okay, and windy, if it's true, we'll predict no, and if it's not true, false, we'll predict yes. And there were 2 cases when this was correct and 0 cases when it was wrong. And here there were 3 cases when it was correct and 0 cases when it was wrong. Okay, so these are pure nodes again. This is a pure node. This is perfect. This rule is perfect for this data set. So if it's outlook, rainy, if outlook equals rainy, sorry, then check windy. If windy is true, we predict no. If windy is false, we predict yes. These are perfect or pure nodes. They don't have any errors in them. They don't have any misclassifications. Okay, so we're separating the data into kind of pure sections. Okay, is this clear? sort of. So you can go back and listen to this again or think about it again to make sure that this makes sense. Okay, so that is basically how OneR works. And from there you can see how J48 works. Okay, any questions about this? Okay, so you will have something to do in this on the next homework set. Okay, the next set of videos. Okay. Okay, now we come to the big deal, and that is, so in our course, we are going to do 2 algorithms in detail because, you know, we can learn how to use Weka and point and click, and we can learn some of the important ideas like we were talking about testing and training and you know, what a model looks like last time and so on. We can learn that stuff, but I think that it's important that you understand some algorithms from the inside out, how they actually work. Now, we can't do all of them. We don't have a long time in this class, so we have to stick with just a few. So we're going to do the one, which is called naive Bayes, and the other is called a neural network. So neural networks are the ones that are most powerful these days, sort of advanced neural networks. So that's why we're going to do neural networks. And the naive Bayes is also popular and powerful and uses a lot of kind of math or kind of probability. And I think that's also good it's good to understand probability, and the naive Bayes uses it completely. So it relies completely on probability. So it's also very good, and it's also used. It's still in use. And for example, I know that I don't know if Google still does it this way, but you know, if you have Gmail, Google will mark your mail as spam or junk mail. They used to use, I don't know if it's still being used, it was naive Bayes that it decides whether incoming mail is classified as spam or not spam. So that's how it's one place that it's being used. Okay, so this is a naive Bayes algorithm, and it's up here. If we go to here and classify, we go to here, and there's a whole set of different versions of naive Bayes or Bayes algorithms. And but the basic one is called naive Bayes. There's also Bayes net. There's naive Bayes multinomial. This one maybe is for text. And yeah, those are the basic ones. So we'll use this one. By the way, in Weka, you'll see these lists of algorithms. Some of them are grayed out. What that means is that they're not appropriate for the particular data set that we have. Like in our case right now, I'm looking at multinomial. I'm sorry, I'm looking at, what am I looking at? The weather nominal. Everything is nominal, right? So there's certain algorithms that won't work with just nominal data, or they might not work with where the output or class variable is nominal. So so anyway, so you can see, for example, this naive Bayes multinomial doesn't seem to be appropriate for the particular data set that we're working with right now. However, naive Bayes will work with it, and let's just try it. So let's just see what it does. So we saw that J48, well, let's just check it. So let's try it. So here it doesn't do so well. 57, and naive, this one does better than this, sorry. But actually, I think OneR did better than, is that true? Let's try OneR. What was OneR? We didn't try OneR, but let's check it. It's under rules, under OneR. No, OneR didn't do very well either. Okay, so BayesNet actually did better. Of these three, it did the best. And I'm sorry, BayesNet? Did I do BayesNet? I meant to do naive Bayes. Oh, I did the wrong one. Try that. Okay, naive Bayes. 57%. So of these three, naive Bayes has done the best. Okay, the other one that we will want to choose study later is called under functions. It's called multi-layer perceptron. That's a neural, what's called a neural network. Let's see how that does. Does much better. Okay. Anyway, we want to talk about naive Bayes today and next time. By the way, we also have to discuss this area down here. These are different ways to measure how well the algorithm performs. Of course, we often use this as the measure, 71%. But these are also interesting and appropriate. For example, let's just think about an example. Suppose there's a COVID-19 test. Okay, so let's suppose we have a COVID-19 test, and so we have people might be, their condition might be that they are sick or they're not sick. And on the other hand, how do I do this? I meant to put this here. Yeah. But we also have a test. The test result might be that they are sick or they're not sick. Does everyone understand that division that I've made here? So maybe I want to put this up here, over here maybe. I don't know. I'll put it there. Okay. So they can be sick or not. I'm sorry, the test result can be that it shows that they're sick or it shows that they're not sick. And their actual condition can be sick or not sick. Does everybody understand this?
Yes, Professor.
Okay, so let's put some results in here. So here's let's say altogether in our group, we have 70 people who are sick. The test doesn't necessarily catch all of those people, right? So maybe it shows that 60 of them are, pardon me, are sick. So it missed 10. So 10 of those people, even though they're sick, it shows that the test doesn't show that, doesn't pick it up. So there's 10 there. And then let's say in the not sick category, let's say there were 30 not sick, and it says let's say 10 of them it shows that they're sick even though they're actually not sick, right? That's possible, right, for a test, right? Tests aren't exactly right. So we get 20 here. Does everyone understand this?
Yes.
So what is this? It's a confusion matrix, right? We talked about confusion matrix, right? Didn't we talk about that already?
Yes, Professor.
Yeah, where is that? That's here, right? This is the so-called confusion matrix. We talked about that. What is this? This is the same thing. This is a confusion matrix. The only thing is I don't know if I put it in the same order that they did. So they have the test on the top. Yeah, I happen to do it the right way, just by luck. So I put this along the top and this along the side. I could have just put this along the side and this along the top. And actually, if you look it up in Wikipedia, they do it the other way. They do it not the way I did it here. But anyway, this is a confusion matrix. What's the algorithm? What's the algorithm? So here, the algorithm is what? J48, right? Or is it J48? Sorry, it's a multi-layer perceptron here, right? Everyone understand? Here's J48. This is J48, right? That's the algorithm. Everyone understand that?
Yes, Professor.
So what does that mean? That's the test that we're using to classify, right? Is J48. We're using J48 as a test to classify, you know, are you yes or are you no, right? That's what we're doing, right?
Yes, Professor.
So what's the algorithm here?
It's the multi-tone perceptron as well.
No.
A48.
No, the test, no. The test is this chemical test that we have that we stick something in your nose and we decide, so that's the algorithm, right? We're putting something in your nose and it comes back and it makes a prediction, right?
Manually.
Yeah, manually, right. Yeah, it's the physical algorithm. It's the physical test that we give. That's the algorithm. That's the thing that's doing the predicting, right? You understand?
Yes, sir.
Right? Well, the algorithm is the thing that does the predicting, right? In here, the algorithm was J48. It did the predicting. Here, it was naive Bayes. Here, it was OneR. Here, it was multi-layer perceptron. Here, what's doing the predicting? The medical test, right? That's doing the predicting. Everyone understand that?
Yes.
So this is also a confusion matrix. Now, what's the error here? Or what's the accuracy? Let's say, what's the accuracy? How many people are in the sample? How many people were tested?
100.
100, right? 70 and 30. Okay. And how well did it do in those 100? How many were classified accurately?
80 people.
80.
What should we use for accurate? Green? Those were classified accurately, right? So that's what?
8 over 10.
80 over 100, right? So that's 80% accuracy, right? And how many people were inaccurate?
2 over
20.
2 over 100.
20 over 100. So what's the accuracy rate? 80%. What's the inaccuracy rate? 20%, right? Everyone agree?
Yes.
Okay, but that's not necessarily what doctors are interested in. And that's probably not what you're interested in either. For example, there might be more interested in here, looking at all the sick people, how many did this test correctly classify? Or how many of not even that. Yeah. Within the sick people, how many were correctly picked up? What would you say?
60 over 70.
Yes, right. 60 over 70. So within the set of sick people, how many were picked up, or in other words, correctly classified? Right? That's kind of a more important question, isn't it? Like, I don't, anyway, I think that's a pretty important question. And the answer is, let's say, what is it? 60 over 70. So that's the rate that probably doctors are most interested in. For example, what is this? What about this? This is, we could say, from the people that were not sick, it made some errors, right? How much error did it make for the people that were not sick?
10/30, one
Right.
third.
10 out of 30, right? But that's not so bad. That's not so, I mean, I'm sorry, that's not so important, right? In other words, what does that mean? If suppose that happens to you. So you're actually not sick, and the test says you're sick. Which case would you rather be in? And let's change this not to COVID, although COVID is pretty serious, but let's change it to cancer instead of COVID. So which would you rather be? Sick, and it makes a mistake and tells you you're not sick, and it says you don't have cancer, or not sick, and it tells you you do have cancer. I don't mean which would you rather be, but which error is more dangerous?
The first one.
In the first one.
Yeah. If it tells you you're not sick and you actually have cancer, that's much more dangerous than if it tells you you are sick and you don't have cancer, right? Because what they can do is give you a second test, which might have a different kind of accuracy, or just, whatever. Anyway, they probably won't kill you in that case, but you might die in this case. So, so we can see that we said that the error was this rate, but I think this error is more important. So it's like 10 out of 60. That error is more important to look at than this kind of error. So we have names for this, and since we started talking about this, we may as well finish it. So let's look up in Wikipedia. Let's look up some names are called precision. I don't know if I can spell it. Precision and specificity. And let's look up here. Here. So we go here, and here are the, so what do we have? The true condition and the predicted condition. So they have just the opposite. I had the predicted condition up here and the true condition down here. So if I want to go back, and by the way, you can do this easily, or sort of easily, in Excel, I think, by copy and paste this way. Now it reversed it. So I put the test result here and the condition over here. So now it looks like Wikipedia. So let's just get Wikipedia. In fact, let's just try and copy the whole thing into my sheet. Maybe what I should have done was copied this one in the opposite direction, but okay. Let's put this here. Okay. So okay. So you can see, so what were we interested in, by the way? This one here, going down here, and we did 10 over, I guess I don't need that thing there. 10 over 60 was one kind of error. Now, but actually the error, so the accuracy wasn't 10 over 60, it was 50 over 60, right? So that is called the true positive rate. Anyway, we have some other things here. Maybe we'll study it later. But if you go this way, or you go this way, or you go down and down, you get different names. And you can see that there's one that's called sensitivity. And there's one that's called, yeah, the true positive rate is also called sensitivity. So sensitivity and where is it? Precision. Sensitivity and precision are two terms that are used often. So sensitivity, I guess, is the one that we just did. So we would say that this test is has sensitivity of 50 over 60, and the precision is, I'm not sure. Let's not do it right now because I want to go to probability. But anyway, these terms are measures of the accuracy in a particular direction, like we said here. And also we can talk about measures of the inaccuracy in a particular direction. Okay, and WECA also shows that here. So we have precision and some other things you can look up here. You can find false positive rate like this, true positive rate, something called recall, which is also in here, and so on. Okay, so anyway, these errors can be more important than just the overall error rate here, depending on what you're doing. If your test has to do with sick people, you know, we could come up with a J48 algorithm that predicts whether people have COVID or not, or predicts whether they have cancer or not. So we take a whole lot of data from their bodies, and then we come up with an algorithm, and it says, oh, you have cancer, or it says you don't. So it doesn't have to, you know, so it could be an actual algorithm like this. And we could still talk about the sensitivity and the precision and so on for that test. So anyway, we have the sensitivity and precision here. And we'll talk more about this later. Okay, but the point is that the confusion matrix will tell us these things, but it will also give us this information. Sometimes we're more interested in this information than this measure. Any questions about this so far? Any questions? Any questions?
No.
Okay, so this is a very important concept, one of the most important. And you'll see when you hear about these new medical treatments, like there's a new COVID-19 treatment called remdesivir, which is supposed to help people who are sick. And they'll talk about the sensitivity and the specificity of the test. You'll hear that frequently. Okay, so you have some idea of what that means, and you can look it up in Wikipedia to understand exactly which one is which. Or you can look it up on Google. Okay, let's continue. Let's take a quick break here. I don't hear too many responses, so I think you're getting something, tired or something. So let's take a quick break. And if you want to ask questions during the break, and then we'll come back. I see my time is 11:38, so we'll come back at 11 in 5 minutes, 11:40. 43. We'll start again. And if you have questions, you can ask me now. And we'll come back and we're going to talk about Bayes, naive Bayes algorithm.
Professor, can I ask a question? Regarding the data that you're using on Weka, what does the precision indicate?
Here? You're talking about here?
Yes.
Okay. Okay. Well, first of all, what we're using, this is, we're using the, yeah. This is the, not the golf data, okay. And so the precision, let's look it up. Precision is which one? All right, let's go back to here. Okay, where's precision? Here, here's precision, right? So what is it? It's the sum of the predicted condition positive. So here's the predicted condition, and the condition can either be positive or negative. And so it's this row, right? So we're talking about this row, and then the true positives, the ones that were the true positive means the ones that were predicted positive, that's the true, and no, sorry, that's the positive, and that they actually were positive. They call those true positives, okay?
Mm-hmm.
So that's this number divided by these two, right?
Yes.
So that's what the precision is going to be, right?
Yeah.
So in our table, it's this is horizontal, but in the way I did it, it would be vertical. So that would be, positive means sick, right? Usually, right?
Yes.
You understand? Right. So
Mm.
the true positive rate would be what we did, 50 out of 60, right?
Yes.
Okay. So now let's go back to Weka. Oh, sorry. Weka doesn't have this. So we go to Weka. I guess the true positive is still going down. So I think it's out of out of this. This is yes. So I think it's 5 out of 8. So let's see. True positive, no. Precision, sorry. Precision, no, no.
Yeah, 5 out over 8 is equals to 0.625.
Oh, you're right. I'm sorry. Right. So this is right. So that's 0.625. And then this one is, WEC is a little bit unusual. Most times this number may not be reported, but in WECA, I guess that's the remaining part, right? I think. No, that's wrong. It's not the remaining part. What is that? I forget what this one is. This is, it's not 3 out of 8, is it? No,
It's 2 out of 6, I guess.
2, oh, right, it's 2 out of 6, right. Where does that come from?
Or B, I guess.
What?
Classified as B.
I think it's 3 out of 9.
3 out of 9. Where's 3 out of 9 though?
So if we see the results for A and B, that's 9, and the results for
This one?
yeah.
Mm,
I have to, I've looked it up before and it's not too hard to understand it, but I don't remember it right now. You can look it up. You can look up Weka precision and you'll find somewhere some explanation. It's a little bit obscure. And then this, so I have to look it up. I don't want to do it right now, but you can also look it up. And then this is the average of those. So this is kind of the weighted average. But normally, that when you have, this is, we only have 2 classes here. The classes are play and not play, right?
yes.
So we only have A and B and A and B. But we might have more. We have A, B, C, A, B, C. Then there's going to be more rows here. And then you have the weighted average. But most of the time for like medical tests, you only have, you know, did the people get better or not? And, or sorry, yeah, right, improved or not improved or something like that. So you might only have 2 cases like we have here. But I have to look it up. I don't remember exactly how to interpret this. So I can't answer that second one. Okay, let's go on to naive phase. Okay, so let's start now. And in this, I provided you this this PowerPoint, and I went through this stuff, sample space, and events, and conditional probability, and then we started sort of from there. But I want to explain it a little bit carefully. I can't spend too much time on it, but we should talk about it. So I'm going to use this thing. And so, you know, let me just do this poll. Let's see if I can get this working. Poll, add a question. If I do this, okay. Okay, so let's see what the answer to this is. Okay, it's looking very good. Okay, so let me share the results. Okay, can everyone see that?
Yes,
Yes,
Okay,
Professor.
so that's
Yes,
good. So we've all studied probably, not all of us, but almost everybody. So I want to, though, we still need to review some basic concepts because, as I said, naive Bayes is rooted completely in probability. So we should review some concepts. let's do that. Okay, so let's talk about probability. But it doesn't seem to work. Oh, there. Okay. Oh, what happened now? Okay, probability. So when we, I say the probability that it will rain tomorrow. Okay, so that's a typical way that we might use the word probability. Or we might say the probability of getting an even number when we roll a die. When we roll a die. So let's talk about this kind of thing is very hard to deal with, but this kind of thing is very easy to deal with. So let's talk about this one. So we talk about a die, right? And the die has dots on it, right, like that. And we talk about the faces of the die, and we say there are 6. And we have we can get a 1, 1 dot, 2 dots, 3 dots, 4 dots, 5, and 6, and we usually put that in a set like this. And if we had, but I guess it's possible to make a die that doesn't have 6 faces. Maybe you can make a die that has 10 faces, or maybe even less than 6 faces. I don't know. And also we can talk about a coin, and in the case of a coin, we can talk about, you can get either heads or tails, okay? And if you toss 2 coins, we can say you could get heads on the first one and heads on the second one. You get heads on the first one and tails on the second one. You get tails on the first one and heads on the, whoops, and do that. And heads on the second one, or you can get tails and tails, right? And if you had 3, you could have H, 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 T, and so on. Okay, so these are different scenarios where we might want to talk about probability. And we have, in probability theory, there was a Russian mathematician, I can't remember his name right now, but he kind of put probability into a very nice mathematical framework. And so basically, we're going to talk about that here, and simple, but nice. And we talk about some important words: an experiment. We talk about a sample, space, and event. So we want to talk about those 3 words: sample, space, and event. So the experiment, so here we would say the experiment is rolling the die. So rolling die. And then here, the experiment is tossing a coin. And here, the experiment would be tossing 2 coins, right? And here it would be tossing 3 coins. So what do we mean by this word experiment? That's kind of the action that you perform where the outcome is not certain. So we don't know what's going to happen when we roll a die. We could get a 1, but we might get a 4, but we might get a 2, 3, 5, or 6. Same thing with tossing a coin. We don't know what's going to happen. It could be H, could be tail. So usually when you talk about an experiment, you might think in chemistry, you have experiments, but even there, when you talk about the word experiment, it means that you don't really know what's going to happen. Like you have a some dish and you're going to pour 2 chemicals in there, and then you don't know what's going to happen. That's called an experiment. So we also kind of use that word here in a similar way, maybe a similar way. So we roll a die, we call it the experiment. So the first thing is the word experiment. Once we know what the experiment is, for example, once we know that we're rolling a die, then we can talk about what can happen when you roll the die. What are the set of possible, and this is where the guy, I can't remember his name, the Russian mathematician, he sort of formalized these concepts of probability. He said, let's make sure that we think of it as a set. So the set of possible outcomes. We just said that the set of possible outcomes when you roll a die is 1, 2, 3, 4, 5, and 6. And we just said that the set of possible outcomes when you toss a coin is heads and tails. So that's what the set of possible outcomes, that's called the sample space. Okay? So the experiment is the action that you perform, and the set of outcomes that you can get is called the sample space. Okay, so we have those concepts. Now suppose, oh, by the way, I want to change this to view, page color, more colors, that color. Okay, so now let's talk about the other word, which is event. So what does that mean in this context? So this is the sample space for rolling a die. This is the sample space for tossing a coin. Sample space, we'll call it capital S. So this is capital S for rolling a die. This is capital S for tossing a coin. So what do we mean by event? So we might say in the event that an even number occurs, you get 1,000 yen. Okay, so what does this mean, this word event? What are we referring to, or what do we mean by this? The event that an even number occurs. What does that mean? When do you win? When do you get 1,000 yen? Under what conditions? Under which conditions would you get 1,000 yen?
I guess when the number 2, 4, and 6.
Yeah, if either 2 or 4 or 6 occurs, then you're going to get the money, right? You're going to get the yen, right? So the event that an even number occurs is this set of the outcomes, this subset of the sample space. The sample space was all the possibilities. This one, the even numbers, is a subset. So that's again what this, I can't remember his name right now, but maybe it will come to me. What he set this up. He said events will be subsets of the sample space. So here's an event, or we could say the event of an odd number. And what event would that be? That should also be a subset. So obviously it's this one, 1, 3, and 5. Okay, so, but the important thing here is to say that events are subsets of S. What do I mean by S? The sample space. And I think you might remember that, you know, if you have a set A is equal to 1, 2, 3, 4, and you have a set B, which is equal to 2 and 4, we say B is a subset of A, right? Everyone know that?
Yes, Professor.
And that the definition of subset means if B is a subset of A, it means that every element in B is also a member of A. And then we just check. Here's an element of B. Is it also in A? Yes. Here's an element of B. Is it also in A? Yes. So B is a subset of A. And we denote that with this. B is a subset of A like that. Okay? So here, let's call this even number. Let's call that A, some event A. And we would say A is, of course, a subset of S, right? This is a subset of, oh, sorry, this is odd numbers. So that is a subset of this, right? And we could call this M. And we could also say that M is a subset of S, okay? So any event is a subset of S, and any subset of S is an event. So I could choose another event, any subset of S. So suppose I just make up a subset of S. 1, 5, 6. Okay, let's call that G. So that's clearly a subset of S. 1, 2, 3, 4, 5, 6. So therefore, G is an event. Now maybe we can't give it a nice name like even numbers or odd numbers or something else, but it's still an event. The event G, okay? Any subset of S will be called an event. Let's just do one more. Let's suppose we talk about the event that you get a number less than 4. You get a number less than 4. So what is that event? It has to be a subset of S. So it's what? 1, 2, and 3. Okay, so that's another event. How about if we're talking about, I guess we should do just a little bit more here. Suppose we talk about toss, the experiment is toss 3 coins. That's the experiment. Okay, so what's the sample space here? Somebody tell me? Remember what we did here for the sample space? We said for 1 coin, HT, for 2 coins, HH, HTT, HTT. So here's the three coins. So it's going to be, you could get H, 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 you could get H, H, T, you could get H, T, H, you could get T, H, H. So that's 3 heads. These are the cases where you have 2 heads, and then you can have a case where you have 2 tails. You get T, T, H, T, H, T, and H, T, T. Those are 2 tails, and then the last thing is 3 tails. So that's the sample space. Everyone agree with that?
Yes, Professor.
So what do we call this? S. Okay, that's the sample space. So suppose I say the event of getting 2 tails. Okay, the event of getting 2 tails, let's call it E. So what is that? It has to be a subset of S. So what is it?
TTH.
TTH,
PHT,
THT,
HTT.
HTT, exactly. So that is the event of getting 2 heads. Okay, now in math, we have a symbol. There are different symbols for it, but one symbol is this. N, you write a set inside. So N of E usually this means the number of elements in E. So how many elements are in E? 3. Okay, how about N of S? How many elements are in S?
8.
8, right. And going back to some other one, how about G? N of G is what?
3.
3. And how about N of A here?
4.
4. Okay, so that means the number of elements in the set. Okay, now suppose that we, okay, so finally, so we just covered the 3 important words: experiment, sample space, and event. Okay, now we get to the questions that we're actually interested in, which is like, what's the probability of getting exactly 2 tails? So what's the probability of this? We said the event of getting 2 tails was here. It's here, E, we called it E. But what's the probability of that? So we don't even decide what we mean by that word. So we have to decide what we mean. So going back to the even and odd case, so suppose we had a die. So it's a different experiment. We're not tossing 3 coins, we're rolling 1 die. So this example, and we talked about the event of getting an even number. And if I ask you what's the probability of that, let's call it E. If I ask you what's the probability of that, most people would give me an answer quickly. What would they say? Uh-oh, we're almost finished, aren't we? Okay, what would they say?
3 out of 6.
Yeah, they would say 3 out of 6. Right. So, and if I asked you, here's another event. Let's call it P. No, not P. Let's call it H. And that is 4. Now, is that really an event? Sorry about that. Is that really an event? Yeah, it's a subset of S. This is a subset of S, so it is an event. So, okay. So if I want to know what's the probability of this event, what would you say for that? So that's the probability of getting a 4. So what's the answer to that?
1/6.
Right, everybody would say 1/6. Okay, so what are we doing in our head to get this answer and to get this answer? First of all, let's get some notation. Let's say when we ask the question, what's the probability of H? We'll write it like this, the probability of H. And if we ask the question, what's the probability of E? We'll write it like this. Okay, so let's just use that. Other books will use different things, but that's very easy. So let's just use that. So, but anyway, everybody readily gave me the answer of 1/6. Everybody readily gave me the answer of that. So you must be doing some calculation in your head so quickly that maybe you don't even think of it as a calculation, but you're probably doing a calculation. And what is the calculation you're doing? For example, for the probability of E, even number, you're doing this. Because you're saying, okay, there are 6 outcomes, and E has 3, so it's 3/6. So the number of elements in E divided by the number of elements in S. And the same thing, same kind of calculation for the probability of H. You're saying it's N of H over N of S. You're doing the 6 here, and you're doing the 1 there, and you get 1/6. So we're going to use this kind of very simple definition of what we mean by probability. Now, it doesn't always work. It's not always applicable, but it works fine for explaining the concept, the later concepts that we want. So we're going to just say that this is called the, I forget, I think it's called the classic definition of probability measure or something like that. Anyway, we're going to use this. So what we mean by the probability of an event is n of that event over n of s. Okay? So now we have the concept of probability. So we have all these concepts: experiment, sample space, event, and probability. Okay, now we can work with, we can ask probability questions. And there are some rules, maybe you remember some of the rules. For example, if you have two events, E and F, let's say E is equal to 1, 2, 3. I'm talking about the experiment of a die, and F is equal to 2, 3, 4. You can talk about E union F because these are sets. These are both sets. So E union F is equal to what?
2 and 3.
No, E union, not intersect.
1, 2, 3, 4.
1, 2, 3, 4.
1, 2, 3, 4. That's right. And E intersect is what?
1, 3, 2,
What is it? 2
3.
and 3. Okay. So we can also then, now notice that this and this are both events. Why? Because this is equal to that, and that is a subset of S. And this is equal to that, and that is a subset of S. So these are both subsets of S. So if it's so there are both events. So this is an event in and of itself. So we can ask, what's the probability of E union F? And obviously, you know, we already decided that it's going to be n of E over n of, or it's going to be n of this thing over n of S. So it's obviously going to be 4 over 6, right? Everyone agree with that? 4 over 6. But can we write it in terms of the probability of E and the probability of F somehow? You know, I can just do it. Yeah, it's 4 over 6, but can I say it's related to the probability of E by itself and the probability of F by itself? So I'd like to say, oh, it's just this, but that's not true. The probability of, now why does it do that? I don't know why it does that. Okay, probably does that to tell me that we're finished. Okay, so we are finished. So we're finished. Okay, so we covered the very basics of probability. We have to go a little bit further. We want to get up to what we call conditional probability, which won't take too much longer. We'll do that next time. And then we'll go through the naive Bayes algorithm. And we might finish it in one class, I'm not sure. I did put it on in Manaba, in the resources, that PowerPoint, and we will go through that next time. Okay, that's all for today.
Excuse me, Professor, is it okay if I ask a question?
Yeah, sure, go ahead.
Tomorrow, for like when it comes to meeting you, we are supposed to present a data set, and at the same time, you know, tell you about the stakeholders and everything.
Yeah, you should be thinking about that because this is your beginning of your project. So you should be, you know, you should have several different data sets because in case one of them, you know, you can have your best one and then backups, okay?
Oh.
And then you should have 3. I think I said you should have 3. But you basically, you only need 1, but I want you to have backups in case the one that you have is not so great. in case we don't agree that it's so great. Then you'll have some backups we can discuss. And then also, you should, you should be thinking about the stakeholders, because we want this to be kind of a practical project. And so practical means there are stakeholders. So you should be thinking about that now.
And present it to you tomorrow.
Yeah, discuss it with me tomorrow.
Okay.
But I just want you to be able to discuss it intelligently. So you could say present it, but I'm not expecting a presentation. I just mean I want you to be prepared so we can make use of the time.
And all 3 members of the group need to be there?
Well, there are some cases people have contacted me and not all 3 could make it. So in that case, we can somehow record it and then you can share it with the other member.
Thank you, Professor.
You're welcome. Anybody else?
Yes, can I have a question?
Yeah, can you speak a little louder?
Oh yeah, I'm the person that I emailed you about my salary last week, and then you said that you can move me to another group.
Oh, what's your name? Oh,
Yeah, my name is
yes.
is
Okay, right.
Yes, and
Right.
I emailed you that I want to.
Ah, right. I remember. Okay.
Yeah.
So, yeah, I
What should
didn't
I do
move
now?
you yet, right? I didn't move you yet?
Yeah, because I have friend in that group, and then they can add me and work right now. So yeah, it's convenient to me for.
Did you move or did I give you a new group? I gave you a new group already.
No, you didn't reply me.
Oh, I didn't. Okay.
Yeah.
Okay. Could you have a few minutes after this class?
Yes, I have.
Okay. So let's just see if there are any other questions.
Yes.
Any other questions? Okay. So let's talk about your group. I have to check that. So your group is somewhere. Where's that? Oh, first of all, let me just do something.